Welcome, everyone. Uh, in between this class and the last one, there it is. Temporarily lost my marker. It's back now, and I'm ready to start. There's some information I want to relay to you first. One slight adjustment as far as the material we want to cover, one mini little lecture, and then the format for today's quiz. Today's quiz will open up during the last 10 minutes of class. And please pay really close attention to what I'm saying here. I just finished the first class. We finished their quiz just 5 minutes ago. And I would say about 1 out of 3 actually have it in the correct format. So make sure you get the format correct when you take today's quiz. All right. So here's the mini lesson I want to give, and we'll talk about the quiz after that. So let's say I'm interested in taking the antiderivative of e to some linear function of x. I mean, we use a lot of this growth and decay stuff. Maybe if it's a money and banking problem, we might have PE to the RT, maybe that interest rate is 0.05 or something like that. So that's a function we use a lot in this class. And I want to make sure we know how to handle it when it's not simply just an x or just a t, but there's a multiplier by it. It's probably not a big surprise what I'm going to do anyway, but I'm going to start with a really straightforward one and build up from that a little bit. Let's say we had the antiderivative of e to the 2x dx. So we're looking for the antiderivative of this function. And before I talk about that one, let's take the derivative first. Let's say if we had y was equal e to the 2x, and I asked you to take the derivative of that, by the chain rule, we would keep that e to the 2x and then multiply it by the derivative of the power. That's one of the chain rules that we used, the one that we're really going to review for right now. Well, the derivative of this linear function, this 2x, is just 2. So this is 2e to the 2x for the derivative. So notice that going from the original to the derivative, we keep the e to the 2x. That stays exactly as it was. That doesn't, so that's just really just a copy thing. The only difference between the function and the derivative is the derivative has a factor of 2 out in front. So thinking forward on this one, if the derivative of this gets multiplied by 2, then the antiderivative, we should do the opposite. So if I were going to find the antiderivative of this one, I would keep the e to the 2x, but instead of multiplying by 2, I would multiply by the reciprocal of 2, and then add the c at the end. So it's sort of like the power rule. We raise the power by 1 and then multiply by the reciprocal of the power. Here we're going to multiply by the reciprocal of the derivative of the power. Okay. So if I had, for example, 185 e to the negative 0.173 t dt, notice I changed my variable from an x to a t on this one. And notice also I have a 185 constant multiplier. So we'll do maybe a step at a time here. 185, bring that out if you choose, e to the negative 0.173 t. So notice that this problem and this problem are pretty much the same. It's just that the multiplier on the variable is a little bit different. So now we will apply the new rule we've just used. We'll keep the 185. Leave a little space here for my new multiplier. Keep the e exactly to that same power. Multiply by the reciprocal of that new power. The reciprocal of the derivative of that power. So 1 over negative 0.173. And then add c at the end. The only work that's left to do is to multiply those two numbers together and find out what that's approximately equal to. So that's today's little mini lesson. We used to have 2 videos, 2 lessons dealing with integration by substitution, and this was sort of a little mini integration by substitution problem that got us ready. That's the material that we've cut out this semester, so we won't be doing that. But this one comes up so often in the material that I had prepared that I thought it'd be worthwhile just to come back and get that one. And again, the exponential function to a linear power happens so often in our modeling. In fact, it happens on today's problem number 1. Problem number 1, by the way, is one of my favorite questions in the entirety of the class. So it really makes us think a lot about what the graph looks like. There's some applications from the first exam, from the second exam, from the third exam. Raining hard on my window now. During the last class, people were outside, asleep. During the last class, people were outside mowing the grass. Things have changed in a heck of a hurry. Okay, so here's the other half. And this, I'm not sure if people weren't paying attention or if they didn't log in, but today's quiz is a fill-in-the-blank type quiz, and there's a format that I want you to use for the answer. So I'll give you a function. It'll have 3 pieces in there. Maybe it'll be the antiderivative. Oh, I have it. There we go. Say 3 e to the x over 2 minus 5 over x plus maybe you say 4 over the cube root of x dx. I think the directions say find the antiderivative. And then when you go to your answer, a place to type in your answer, there's a little menu here. One of the items on the menu is the math symbol. I had a word for it, I can't think of it anymore. Anyway, there's sort of a little bit of a cursive F and then an X right next to it. Equation editor, that's it. So that's the button that you push to get to the equation editor. Okay. And once you're in the equation editor, I think the main button really has all the tools you're going to need. There's a parentheses there, there's an exponent button there, there's a fraction button there. And by the way, when you use the fraction button, use the one that has the horizontal line. Don't use that fraction button, and I'll show you why in just a second. So when you take today's exam, you should push this button. A little window will pop up. It'll be marked LaTeX because that's a sort of computer program that works in here. It's a nice program that puts things exactly where they should be, and that's the format that we put in a number of your exams in this class. I know the finalists is written in LaTeX. It's a very handy program for making mathematical things look really, really nice. I want you to use that, okay? If I were to take this antiderivative, by the way, and I'm going to do it, and then I'll show you the 2 different ways that this answer looks. So if I were to do this one, I would have done it 3 halves e to the x dx. There's the first one, minus 5 antiderivatives, 1 over dx. There's the second one. I can move these apart, by the way, because of the plus minus rule. And then 4 antiderivatives, x to the negative 1/3 dx on that one. And now apply the appropriate rules. So this is 3 halves e to the x minus 5 natural log absolute value of x. The absolute value sign, by the way, is on that first menu. You can find it easily. Plus, let's see, 4, keep the x raised the power by 1, multiplied by the reciprocal of the new power, and then add c. So in the final form, this is 3 over 2 e to the x, or if you want to put 3 e to the x over 2, that's fine. Minus 5 natural log absolute value of x. Again, if you're not into this LaTeX, you're not going to be able to write the absolute values. Do the multiplication here. This is 6 cube roots of x squared plus c. So when you find that button, you should be able to get the equation that looks like that. Again, on the fractions, make sure you use this one and not the one that's tipped sideways. Otherwise, that looks like this. And then I don't know whether you have that e to the x in the denominator or not. In fact, as it's written, it would be, I guess it would be in the numerator, but it's unclear, okay? If you use this one, then I know, or if you were to write this as 3 e to the x over 2, then I know, but I have to make sure that I know that you know what's going on. Okay, so here's what people did. They didn't listen to me, they didn't push that button, they came up with the derivative. And they tried to type in as best they could 3 over 2e hat x, without that thing, minus 5 natural log, and maybe they did absx plus 2x hat 2 over 3 plus e. That's not what I want. I want it to look like it's supposed to look. So make sure you use that equation editor. Okay, what time will the quiz open? The quiz will open the last 10 minutes of class, and we're going to stay consistent with that the rest of the way through, Jessica. So the quiz will open precisely at, I guess, 4:50 for this class. Yeah, I have it set to open at 4:50. That reminds me, I'm going to double check to make sure that it's available, because I know last time we had just a little bit of an issue. I'm feeling a lot more confident in my abilities to make this work as I wanted to, but I am going to check it out. By the way, I sort of wanted to use this method on exam number 3, but I knew it was complicated enough that students might not find it. So I sort of put off the introduction of it until we had something with a little less importance, I guess. So there's quizzes and tests. Yeah, 4:50 today. They'll be available then. Let me make sure I have it available as well. Last time I had everything set, but I missed the availability. Available to students, yes. All right, so it is definitely set and ready to go. All right. Well, again, find that button. It's written on that little menu bar. As soon as you go to type your answer in, it's written right above there. Find that button and enter the equation so that I know that you know what's going on. Okay, with that said, I'll take any questions anyone has over activity 19, or really any questions anyone has over anything as far as the class has gone so far. Problem 2A through 2E. All right, here we go. I guess you had 2E typed in earlier, didn't you? Okay, this is an excellent one to look at. If I were to label this graph, this is the power. That's measured in kilowatts here. And this is the hours that the factory has been at work, and this is, I guess, the time, and that's measured in hours. So the hours, kilowatts. Power, if you think of, let's say you're going to get a little exercise. The power you would use, let's say you're going to go run. The power you'd use would depend on how fast you're running. If you're sprinting, then the power is high. If you're just jogging, then the power is low. Okay? If you're sprinting and you run for a long time, you're using a lot of energy. If you're just jogging and you go for a long time, you're using less energy. The area under the curve is the energy. It's the power times how long you apply that power. So if you're running at 10 miles an hour for an hour, that's the same amount of energy as 5 miles an hour for 2 hours. All right, there's like a product between those two. So those are the units. And when you go to calculate the area here, the height will be so many kilowatts, and the time will be so many hours. And this is a really important aspect of this that everyone has to get, because otherwise your answers make no sense at the end. The area in each of these rectangles, or the area under the curve, is going to be measured in units of always whatever this is, multiplied by whatever that is. Remember, on derivative, it was the input divided by the output. Now we're doing antiderivatives. It's the product of those two. So there's kilowatts, there's hours. These units are going to be kilowatt dash hours, not kilowatts per hour, kilowatt hours. So when there's a multiply involved between variables, we generally put a dash in there. That's a universal symbol that we're multiplying those units together. If you look at your energy bill, those of you who have an apartment where you pay for your own electricity, kilowatt hours is how that's measured. How much power do you use by how long that power is being used. Okay. There's not even part A, but I wanted to make sure that we get these units right because that's been a struggle over the last several years. Part A, where's part B? There's no part B. Each rectangle will account for how much energy. Okay, so each rectangle, it looks like it's 1,000 kilowatts tall and 1 hour wide. So each of those little rectangles that you see on your grid will be 1,000 times 1. They will represent 1,000 kilowatt hours, not kilowatts per hour, kilowatt hours. Okay. Estimate the energy requirement for the hours 5 to 10. So I'm going to do my best to recreate the graph. It's not going to be perfect. It doesn't really matter because I've asked to estimate. So from 5 to 10, let's see, we start out here. It looks like we're pretty much straight down. Then we're concave up. Get up here, we go concave down. Increasing, decreasing, increasing. That looks decent enough. From hour 5 to hour 10. Okay. So I can tell what the power was at hour 5. That was right about 2,000 kilowatts. The power after 10 hours was right about 9,000. So somewhere in between, if I were to count up all those little blocks, I could figure out what the energy requirement was. So that's what I'm going to do. I'm going to count the little blocks under there, realizing that each of those blocks is 1,000 kilowatt hours. So I'm going to count, see, there's 1, 2, I guess there'd be 5 of them over here, 3, 4, 5, 2, 5, 6, 7, 8, 9, 10. The next row is 11, 12, 13, 14, 15, 16, 17, about 18 on the next one, 19, 20, 21, 22, 23, 24, 25. I guess maybe about 26 blocks. If I wanted an estimate on that, so 26 blocks times 1,000, I would guess about 26,000 kilowatt hours for part C. And now I've forgotten how far I was supposed to go. 2A through E. Can we do problem 1? Sure, I'll get to problem 1 in just a second. Let me finish this one up, A through E. Another way that you could have got this, by the way, and this is a handy, find my green pen, there it is. You can sort of shoot for the middle in between the high and the low, maybe right about there, and say it looks like for an average value somewhere between, I don't know what that would be, maybe right about 10, 9, 8, 7, 6, right about 6,000 would sort of split the difference between the high and the low, and 6,000 kilowatts multiplied by a total of 5 hours, hey, that brings us back to about 30,000 kilowatt hours. So somewhere between 26 and 30, I think, would be a decent enough guess. And again, it's just an estimate. So now we go on to part D, use calculus to find the actual energy. We have to go through part E, okay? I guess that's the whole, no, yeah. Find the calculus, yeah, to 5 to 10. Right, so what we want to do is find the area of the curve between 5 and 10. We want to do better than estimate it. We want to know exactly what that energy consumption is going to be. So to find the area under the curve, we set up the definite integral. We're going from 5 to 10. We're given a formula for the curve, so let's write that formula back in. Now for a definite integral, remember there are two steps. First we find the antiderivative, and then we evaluate by taking the function from the top minus the function from the bottom. So the antiderivative goes first. 5.5 is a constant multiplier. I'll bring it along. Keep the t, raise the power by 1, multiply by the reciprocal of the new power. And just continue on that same trend. 100, keep the t, raise the power by 1, reciprocal of the new power. Negative 300, keep the t, raise the power by 1, reciprocal, new power. And on we go. 1300 times a half t squared. And then what function, oops, forget my dt. Don't forget the dt. Remember what value, our value or variable is. 7,000 t. I could put a plus c at the end of it. I don't have to because it's a definite integral. And I end up doing a plus c at the top and a minus c at the bottom when I evaluate. So I'm going to plug a 10 in there. I'm going to plug a 5 in there. Plug a 10 in, you get a certain number. Plug a 5 in, you get a certain number. And then you subtract the 2. I don't think we did this on my 215 class. So maybe we should give this a try. As I recall, I had Wolfram Alpha do this calculation for me before my 215 class. And if I'm not mistaken, it was somewhere around 26,000 total kilowatt hours. So someone, if you'd be so kind, grab the calculator, plug the 10 in, each of the numbers across, tell me what that number is. Someone else start working on the 5, tell me what that number is. And hopefully when we get all those calculations, all those numbers crunched, we'll get somewhere around the 26,000. So again, grab out the calculators, go to it, show me what you got for those two values. If there are any questions about what I did so far, give me a shout out in the chat. Okay, so that seems reasonable, yep. Right around 45,000 for that, okay. Yeah, it should come out pretty nice too. Oh, by the way, I could straighten these out a little bit. Do that, that's just negative 11, that's nice. 100 divided by 4 is 25, that's nice. 300 divided by 3 is a nice round 100. Makes that job a little easier. Half of 1,300 is 650. Makes the calculations go a little smoother. I chose that function just because the antiderivative looks a little nicer. Got the same for 5. Okay, 18,437, 18,438. That seems reasonable as well. And when you subtract the one from the other, do you get somewhere around 26,000? Yeah, you would. You get 26,562. If my mental subtraction is right. Okay. So plug in 10, you get this. Plug in 5, you get that. And I'm fairly sure both of those are right. If anyone gets anything different, let me know. Sometimes the signs get a little confusing on this one, but that just seems spot on to me. Okay. So there we have part, whatever it was, D. So we use this many kilowatt hours. And now one of the most important things, if you're going to understand what's going on, one of the most important things to know is how we're going to get the very next piece. What is the average power requirement? Find the average power requirement from hours 5 to 10. Okay. And then we're going to represent that with a horizontal line. Good, I got my green marker there. We use this many kilowatt hours. Sometimes the power level was low, sometimes the power level was high, but we use that over 5 hours. So if we take 1/5 of that, that will be our average use per hour, right? We've used that much in 5 hours, the 1/5 of it will be that per hour. So we're going to take this number and divide it by 5. This one I think I can do mentally pretty well, close to where it has to go. 5, 15 would be a 3, comes out even, a 1, about a 2. So that's reasonably close. So I took this many kilowatt hours. Again, this is my part D. I'm dividing it by 5 hours. Notice the hours units cancel, and I'm left with kilowatts. What's the average kilowatts? Okay, so I read across my graph. I look to see where 5,312 is, and I draw that line right across there. So some of the time we're using far less than 5,312. In fact, if I were to take a look at that sheet, looks like at time t equal 5, I'm right about at 2,000. And at time t equal 10, I'm almost up to 9,000. So we're up to almost 9,000 here. Minimum requirement was just a shade over 2,000. So certainly it would make sense that my average usage would be somewhere pretty close to in between those two. So 5312 is what the average kilowatt hours come out to be. Now, it's not the average of those two numbers. That would only be true if this was a straight line connecting those two. This one's got a little bit of a bulge to it. We're using more than half, more than the average number of those two for quite a while. So what's the solution to that? 5312. If you take 5312, the average usage for those 5 hours, we're right back to that many kilowatt hours. So how do I go from the total energy used to the average power? There's the total energy used. I divide it by 5 for the 5-hour period, or I multiply by the fraction 1/5. That's the average usage. The total is going to be, whenever I do a definite integral, the units are going to be these times these. The average value of the function is same units as we have on the y-axis. It's that many kilowatts. So once we get all that straightened out, that'll ease a lot of confusion on the next exam. There's 2 problem spots on exam number 4, and one of the huge ones is units. The other problem spot was integration by substitution, which we're not covering this semester. Since we cut a couple lessons out due to the fact that it took a while to get us adjusted over. But the units, I want to make sure everyone has these units this time. So we'll do a couple more problems as we move forward, knowing what the average value is, and hopefully you can understand how this average all comes into play. When I draw that average across here, notice it's taking some of this hill off and adding something to the valley. This area right here, that little extra fill, if I've done that correctly, that should have the same area as this other black cross-hatched area here. In other words, if this is like a hill and you want to level it off, if you push that amount of dirt right into there, it should make it perfectly level. So on some of the examples, I'm going to give you a graph and say, or eyeball what the average would be. All right, so that's all the way through part E. Whew, excellent question to ask, and one that's caused so much concern all the way through. So what's 2F then? Oh, excellent. Well, 2F is going to be how much we use for the first, how many hours was it? First X hours? Yeah. Well, if I I wanted to find out how much was used during any time period, it's always the definite integral from when I start until when I end. If I'm looking for the average for the first X hours, I'm going from my zero mark when I first open the factory and get it going, from zero out of here to some random X. Maybe it's 4, maybe it's 7, maybe it's 12. So my antiderivative here, or my definite integral, would be from 0 to X. So I take my antiderivative as I had before, which is negative 1.1 t to the 5 plus, what was it, 25 t to the 4 minus 100 t cubed minus 650 t plus 7,000. I evaluate that first off at t equal x, and then I follow that up at t equal to 0 in this case. And this one, whoops, I need a t there, don't I? 5, 4, 3, 2, 1. And now my powers are right. And this is the easy one, is the second one, because when you plug in 0 for each of these terms, they all go to 0. So how much energy would be used during the first X hours? Negative 1.1 x to the 5th, 25 x to the 4th, and so forth and so on, all the way down to 7,000 x. Want to figure out how much was used in the first hour? Plug in x equal 1. The first 2 hours, plug in x equal 2. First 5 hours, plug in x equal 5. So that really, I think, wraps up all of problem 1 with a little extra information just so everyone is right on the same page. Okay, let's define activity 1. You probably meant problem 1. So let's take a look at problem 1. So problem 1 is so similar to what I covered on the last video, only this one makes more sense in the real world. When we drop a rock off something, the wind resistance is fairly negligible for a long time, but after a while, the wind starts slowing that rock down too. It reaches what's known as the terminal velocity. It's at the point where the wind pressure is equal to the force of gravity. The wind force and the force of gravity are the same, and it won't go any faster. Same thing happens with a person, only generally it depends on how splayed out you are. But generally, you hit that terminal velocity a little sooner. You start slowing down a little quicker. So if we neglected the wind resistance, then the velocity would just go in a straight line. But with that wind resistance, it starts out nearly straight, but then it curves and then it curves and curves quite a bit more as you go through. So here's my velocity. That was measured in feet per second. This was the time from when my sky jumper jumped out. This is the time t in seconds. And any area under this curve will have units of feet per second multiplied by seconds. Right? Area is length times width, if you want to think of it that way. So it'll be these units times those units. Notice the seconds cancel. So all area under the curve will measure the number of feet that skydiver has fallen. Label x-axis, done. V of 10, what is it? Well, V of 10, we plug the number in the calculator and you calculate it out. I'll let someone do that. I'm guessing, looking at the graph, it's probably 150 some, 153. Someone with a calculator helped me out on that one, plug in the 10 and figure out what it is. And now we're going to write a sentence for that. 10 seconds after departing, forgot what my skydiver jumped out of. I think it was a balloon, wasn't it? Yeah, that way she's not moving sideways. It's just 10 seconds after departing the balloon. Her speed or her velocity. Physics instructor would hate me now because I'm using those two interchangeable. Is 153 feet per second. In other words, when I read in 10, I get back about 153. Did someone do that calculation for me? No, not yet. So someone tell me exactly what that number is. I'm just guessing looking at the graph. Someone plug that in if you'd be so kind. Next part. V prime of 10. Well, V prime of 10 is how quickly that velocity is changing. Right now it's at 153, a little later it's 160, a little later after that it's 170. So that velocity is definitely increasing. So we should get a positive number here. Notice the slope is positive. And one more time, notice the units. Okay. When we take the derivative, the result is these units divided by those units. When we take the antiderivative, it's just the opposite. It's the product of those two. So I'm going to write up the derivative. Well, maybe I'll start with the original function. V of t was equal to 185 minus 185 e to the negative 0.173 t. I have that one memorized. I've done it so often today. Time for the first derivative. V prime of t, derivative of 185, either added or subtracted off is nothing. That's gone. Equals negative 185 is the constant multiplier. Keep the e, keep the power, negative 0.173 t, multiplied by the derivative of that power, negative 0.173. There's the derivative. And again, if someone would be so kind and take a little time, multiply those two numbers together so I have a nice formula here without a double multiplier in it. Okay, so let's see if anyone got that first number. 152.2. Okay, sure. So my 153 was a pretty good estimate. 152.2. So that's how fast they were moving originally. I'm sorry, after 10 seconds. So what did we get for a multiplier of those two? Anyone get a chance to do that? Negative 185 times negative 1.73. What's that come out to be? Oh, I have it here. It's 32. Nice. I guess I did that in the last class, and I have my calculator on my screen. It's 32. Good. Hey, 32 feet per second. That's a nice number to have. Okay. Now we're going to plug in t equal 10. And see what we get on that one. Go to online calculator maybe. 32 to the negative 5.67. So you plug in t equal 10 and you get about 5.67. So when we move, in other words, when we move from 10 to 11, the speed should go up just about that many feet per second. Now let's get our second sentence written. The derivative, the marginal analysis function, always runs the same as the original function. We start with the interior, or the inside variable. 10 seconds after departing from the balloon, her speed or velocity increased, not what it was, but now it increased. And derivatives tell us the rate of increase, increased at a rate of, now we have to get these units right, 5.67 feet per second. In other words, 1 second later, her speed is going to be 5.67 feet per second faster. It used to be about 252.2. A second after that, it'll be about 257.87. So how quickly is her speed changing as the time changes? In the very beginning, when t was 0, this was 32 feet per second. She's gaining speed quickly, but now her change in speed is growing a little more slowly. Yep, 5.67. Excellent. So there we have it. That's all the way through the first several of those. We have v of 10, old news. We have v prime of 10, old news. Now the terminal velocity is what's their speed going to get closer and closer to. And basing what I know on that graph, I can tell after a while her speed hardly changes. That graph flattens out. The derivative gets closer and closer to zero. It never goes all the way and starts coming down again. But what's your speed getting closer and closer to? And I would guess it's right about 185. Now, what am I going to base that guess on? Well, basically, I'm going to look at the line, but also I could analyze the equation a little bit. And if I analyze the equation, it'll show me directly exactly what that terminal velocity would be. So I'm interested as time gets bigger and bigger. Here's really what I'm asking. I'm wondering the limit as t goes to infinity. In other words, as I go further and further off to the right, granted she's not going to be able to go an infinite number of times before she pulls the ripcord because she's either A, going to smash it into the ground at a quick speed, or I guess that's a limiting factor there. She has to pull that ripcord sooner or later if she wants to slow down and make a good landing. But here's our function, 185 minus 185, and I'm going to rewrite this as e to the positive 0.173t. Now, as t gets bigger and bigger, that denominator gets bigger and bigger. This fraction gets closer and closer to zero. So the limit as t goes to infinity, this is just 185. Again, as t gets bigger and bigger, that number subtracted off gets closer and closer to zero. So I can look at the graph, or I can consider a limit like we did way back before exam 1. So problem number 1 has labeled the axis. That's from exam 3. Part B and C is from exam 2. Part D is from exam 1. Without doing any calculus or evaluation, what can we say about the value of the first derivative on our interval from 0 to 40? Since that's what I've drawn here, what do I know about the derivative? Well, I know the derivative at 10. I figured that one out. It was 5.67 or something like that. Tell me, what do I know about the value v prime of t on that interval from 0 to 40? What do I know about v double prime of t? Again, on that interval between 0 and 40. Did I use open or closed in open brackets? So going from there to there, what do I know about the value of the first derivative and why? What do I know about the value of the second derivative and why? So this is coming up again, straight from what we did the last exam. So just looking at the graph, I want you to be able to answer those two. Think back to what we covered last time. Yeah, the function is definitely increasing. Yeah, there's no doubt. There's two things I notice, huh? The function is increasing, and what do I notice about the concavity of the graph on the interval from 0 to 40? So since the function is increasing, what does that tell me about one of those? And then consider the concavity, and what does that tell me about the value of either the derivative first or the second? So the function is definitely increasing. I can see it never reaches a peak and drops back down. It's definitely concave down, right? So we have a function that's increasing and it's concave down. So what does that tell me about this? And what does it tell me about that? So we've analyzed the shape really well. Now we have to go back and figure out, how do I answer those questions? That's always been a tricky thing. I think we were doing that still when we were on campus. The last activity or so dealt with ideas like this. So the function is increasing. What do I know about one of those derivatives? Good. Yep. And the first derivative is positive. Second derivative is less than 0, or it's negative, right? Increasing graph, first derivative is positive. Concave down graph, second derivative is negative. So does that wrap up? Yeah, that wraps up problem 1 all the way from part A through the end. Wow, we got through problems 1 and 2. That's good. 215 class, we didn't quite make it through all parts of those. Are there any more questions regarding maybe something on page 3 or page 4? Well, I guess we did page 3, didn't we? I guess the only thing left is page 4. Any questions on page 4 or any questions regarding the quiz coming up? One continued. Did I not finish one? Okay. Oh, maybe I did. Oh, right. There's the next page. Duh. Okay. Lightly shade the portion of the graph. No, many things are going fast. Lightly shade the portion of the graph that deals with how far our skydiver fell during, what was the first 5 seconds? Yeah. So in the beginning, her speed was really fast. Her speed was increasing really fast. She was going 32 feet per second. So after a second, she was going about 32 feet per second, average right around 16. Figure out how far she went. So the area under that curve, that will be how far she went during the first 5 seconds. Using your counting skills or geometry, estimate that distance. So we need this area under the curve, and there's all sorts of ways you could do it. You could look at each of those little blocks and then attempt to count them. And each block would see 1, 2, 3, 4. each block is 5 feet per second tall and 1 second wide. So if you count every little single block under there and then multiply that by 5, because each block represents 5 feet of fall, you could do that. Another way is you could estimate that using geometry. This isn't a straight line, but if I do put a straight line from here down, I could calculate what the area of that triangle is, and then maybe add, what, 10% or so, because obviously there's less area under this green curve than there is under the black. So maybe let's try that approach, huh? Let's figure out about what that area is under the green curve, and then maybe add 10%. So that triangle that's under the, we should put it in green, huh? Let's just focus on that. I noticed that it's, what, 5 wide, first 5 seconds wide. What would it be right at, what would the y value be at 5? It looks like it's 110 just about. So it's about 110 feet per second tall. Formula for a triangle is 1/2 base times height as far as the area is concerned. So 1/2 times 5 times 110. Half 110 is 55. 5 times 55. 25, carry the 2, 25. 275. And that's short a little bit, so let's add 10% to it. Let's add 27.5 to it, and we get right at 302.5. And again, all we have to do is estimate. We don't have to get it exactly right. So that would be my estimation. It looks like she traveled about 302.5 feet in that 5-second interval. Okay. Or another way that you could interpret it is, well, what's about her average speed? She ended up at 110. She started at 0. So the average speed would have been, what, 55? And give or take some if it were a straight line acceleration. So again, 55 times 5 is the 275 again. So our average speed must have been a little bit bigger than that. Okay, we've done our counting skills or geometry skills. Either way you do it, I think that's a decent enough estimate. Using your calculus skills, find a representation for the distance. So we're not asking for the distance yet in part H. So a representation for the distance will be exactly the area under the curve. And the area under the curve we learned from the last video, we can do by taking the definite integral. Definite integral in this case is going to go from 0 to 5 of whatever function we're measuring. In this case, it was 185 minus 185 e to the negative 0.173t dt. That's exactly the area under the curve, which is exactly how many feet our skydiver has fallen during the first 5 seconds. So I'm going to take this one apart. I can because it's a negative sign. And temporarily, I'm just going to ignore the 0 and the 5. We'll concern ourselves with the antiderivative first. So let's see, 2 parts. I would say I'm going to look for the antiderivative of 185 dt. I use dt because t is the random variable. Minus, I'm going to pull this 185 out front because I can, e to the negative 0.173t, and again follow that with dt. So be careful here when you take the antiderivatives, because when you do, there's no longer an antiderivative sign. Antiderivative of 185 dt, what function has that for the derivative? 185 times, whoops, got a little excited right at my t, 185 times t. Okay, bring that minus along, bring the 185 because it's a constant multiplier. And now we have this little piece to take the antiderivative of. Oh, my English was okay there. I remembered how to do that because that was the first thing I introduced to you today. Keep the e, keep the power, negative 0.173t, but multiply it by the reciprocal of the derivative. So instead of, remember, taking the derivative, we just multiply both. We multiply by negative 0.173. So now it's the reciprocal. 1 over negative 0.173. So again, the opposite steps on the antiderivative. 185t minus that'll come out to be a plus. Oh, and now we have something that I'll probably have to grab my calculator on again. I'm going to grab yours as well, see if we get the same number. 185 divided by 0.173. 1069. I remember that from earlier. So there's the antiderivative. I'm interested in how far that skydiver fell from 0 to 5. I could really, at this point, plug any numbers in there that I wanted. Could rewrite the problem with these. But in this case, we're going to evaluate that at 5 and evaluate that at 0. So now I'm going to need a calculator out. So get busy here. Take 185 times 5 plus 1069 e to the negative 0.173 times 5. Subtract off from that the value we get when we plug in 0. And I'll do that second part for you because it's easy. If I plug 0 in here, I get 0. If I plug 0 in here, I get e to the 0, and e to the 0 is 1. So this is 1069. Someone with a calculator, please run this number through and let me know what you get. Here's our antiderivative. Plug in t equals 5. Plug in t equals 0. What do we get when we plug in t equals 5? $1375.26. Yeah, let's keep it right there, huh? Since the other one is to the nearest whole. 1375 minus 1069. This will be to the nearest foot, I guess. And that's subtraction 6. Have to borrow 6, 9. Yep. Now, the estimate we had just a second ago was really, really close, wasn't it? So she fell about 306 feet during that first 5 seconds. If I asked you now to calculate her average speed during those first 5 seconds, we could do it. Average speed would have been what? 306 divided by 5, which would have been 61.2. So right up here at 61.2, that's where you would mark the average speed. Yeah. 306 feet, nice. So close to our estimate. On then to the next part. So we've done most of the work here on this one. Using more calculus, find the distance she fell during the first n seconds. Well, the only difference between that one and the previous one we did and this one is our limits have changed. So instead of our antiderivative or definite integral going from 0 to 5, in this case it's going from 0 to n. So instead of plugging in 5 for the top part, we're going to plug in an n. Plugging in 0, we're still going to get the 1069. So there's our formula. That's how far our skydiver will fall for the first n seconds. First 5 seconds, you plug in 5, right? First 4 seconds, 4 plug. First 0 seconds, 0 hopefully. First 10 seconds until she pulls the ripcord. Problem 1, all the way done. I promise you this time. Last time I thought I got there a little quick, didn't I? Looks like the quiz is about going over the long weekend because you don't have to jam a whole bunch of new material in with a bunch of old material. So make sure that you have this one in really good stead on Monday. Then Monday we can talk about this, or we can talk about activity 20, which I'll have open as well. Do note on Blackboard, I have listed the sort of the day-by-day planner so you know exactly what's coming up. I'm sure I can stick right to that planner at this point. I've taught this course enough times. I've gotten a good handle as to what this group can do with this distance learning as well. You push that button marked FX, cursive F, smaller x, the x is in the subscript. It'll open up a brand new window. Have power function. You'll have fractions. Make sure you use this one. Do not use this one. I think this very last one has the natural log function. Feel free to just type in LM, okay? All right, so that should open in just a couple of minutes. Good luck with that. And we'll talk to you again on Monday. And you're welcome, both of you. Good luck on today's quiz.